It is, it's pretty wild to think about, but the absolute deepest hole humanity has ever managed to drill into the Earth reached about 12 kilometers down.
Right, the Kola super deep borehole, 12
Well,
kilometers.
exactly, 12 kilometers. And I mean, to put that into perspective for everyone listening, the distance to the very center of the Earth is roughly 6,000 kilometers.
Yeah, it's a massive difference.
It is. That 12-kilometer hole is basically just a literal scratch on the surface of our planet. The vast, overwhelming majority of the Earth's interior is just completely, totally inaccessible to us.
It really is a profound realization when you stop and think about it. I mean, we have mapped the surface of the moon in incredible detail, right? We have rovers driving around on Mars right now.
Yeah, sending back high-def photos.
Exactly. But the ground right beneath our own feet remains essentially an alien world. We simply cannot reach it with our current technology, and honestly, we likely never will.
Which is exactly why understanding volcanoes completely changes how you see the planet. We're doing a deep dive today into how they actually work, and our mission is to sort of demystify the whole process.
Yeah, assuming zero prior science background, we're just going to break it down.
Right, because volcanoes, they aren't just mountains that occasionally breathe fire, They are literal windows to the center of the Earth. They deliver material from depths we could never even dream of digging to.
They're pretty much our only physical messengers from the deep Earth.
They bring that deep, hidden unknown right up to the surface for us to look at.
They do, but to really interpret what these messengers are telling us, we actually have to start by tearing down a very, very common mental image.
Oh, yeah.
Yeah, of what actually sits beneath a volcano.
I think we all have a very specific picture in our heads, right? Like from movies or middle school science diagrams.
Definitely. The classic underground cavern.
Exactly. You picture a volcano, and underneath it, you imagine this giant, glowing, underground swimming pool of liquid magma, just, sloshing around in a massive cave waiting to erupt.
Right, the underground lake of fire. It's a striking image, but modern geophysics paints a totally different picture.
Oh, really?
Yeah. Magma chambers are rarely these big tanks of purely liquid rock. Instead, they are much closer to a hot, mostly solid crystalline mush.
A mush.
Yeah, a mush. The melted liquid part is actually just distributed through the tiny gaps and pores between the solid crystals of rock.
Wait, so it's less like a cavern filled with liquid lava and more like, I don't know, one of those slushies you get at a gas station.
That is actually a really great analogy.
Because it's mostly icy crystals.
Right.
With just enough liquid syrup in between to hold the whole thing together.
Exactly. A very, very hot slushy. That is a highly accurate way to visualize it. Underneath a volcano, this mush just sits there, mostly solid and totally immobile.
So how does it erupt then if it's just stuck there?
Well, eruptions usually happen when that mush gets mobilized. Often, what triggers it is a fresh batch of incredibly hot, truly liquid magma arriving from much deeper down in the Earth.
Oh, I see.
It shoots up into the chamber, heats up the slushy, destabilizes the entire system, and that forces the material up to the surface.
Okay, so tracing this back a step then, where is that fresh, hot liquid magma coming from in the first place?
A good question.
Because, I mean, the Earth isn't just a liquid ball on the inside, right? The mantle, that massive, thick layer just beneath the crust, that's actually solid rock.
It is solid rock, yes. It's incredibly hot, way above its normal melting point at the surface, but it remains solid.
Because of the pressure.
Exactly, because of the immense crushing pressure of all the rock resting on top of it. It does flow, but it flows incredibly slowly.
Like how slowly?
Like warm plastic over millions of years.
Wow.
So it is absolutely not a liquid ocean of magma down there. To get liquid magma to fuel a volcano, you have to actively find a way to melt that solid mantle rock.
And there are a few specific ways the Earth actually manages to melt that solid rock.
Right.
Right? Because changing the state of rock under that much pressure must take immense geological forces.
It does. There are basically three primary mechanisms, and they dictate the exact kind of volcanoes we end up seeing on the surface.
Okay, what's the first one?
The first is called decompression melting.
Decompression melting.
Right. Because that deep rock is under enormous pressure, the molecules are just forced to stay packed together in a solid state, even though the temperature is insanely high.
Right. The heat wants to melt it, but the pressure won't let it.
Exactly. So if you simply reduce that pressure, the rock can suddenly melt without adding a single degree of extra heat.
Oh, it's like taking the lid off a pressure cooker.
Yeah.
The heat was already in there, but the pressure was keeping everything contained.
That's the core of it, yeah. This happens mostly where tectonic plates are pulling apart from each other. When the plates separate, the pressure on the mantle right underneath them is relieved. We see this at mid-ocean ridges, deeply underwater, and at continental rift valleys.
Like the one in East Africa.
Exactly, like in East Africa, it is actually the most voluminous form of volcanism on the planet.
Really? I feel like you never hear about it.
Because almost all of it happens unseen in the pitch black on the seafloor, so it rarely makes the evening news.
Okay, well, pulling plates apart to drop the pressure makes perfect logical sense.
Mm-hmm.
But what about the most famous volcanoes? Like the ones on the Pacific Ring of Fire?
Ah, subduction zones.
Yeah, because those happen where tectonic plates are crashing together, right? Pushing the pressure up. How does an increase in pressure result in melting rock?
It doesn't, actually. And that leads us to the second mechanism, which involves adding water.
Adding water?
Yeah. At subduction zones, one tectonic plate is shoved underneath another, and it dives deep down into the earth.
Right.
As that huge slab of ocean floor gets pushed down, it carries water with it.
Wait, hold on. I have to pause on that.
Sure.
Because that sounds completely backward to literally everything we experience in daily life.
Yeah.
I mean, if I want to stop something from burning or melting, I throw water on it.
Right. Water puts out fires.
Yeah, water cools things down. How on earth does adding water melt solid rock?
I know, it is deeply counterintuitive until you reframe how you think about the water down there. We aren't talking about water acting as a coolant. We are talking about water acting as a chemical catalyst.
A chemical catalyst?
Yes. The water is actually chemically locked inside the minerals of the rock itself. And as that descending plate gets deeper and hotter, it literally sweats out that locked-in water into the solid mantle wedge sitting right above it.
Oh, wow. It sweats it out.
Yeah. And when you introduce water into the chemical structure of superheated solid rock, it substantially lowers the melting point of that rock.
Oh, I see. Okay, it's like throwing salt on an icy sidewalk.
Exactly.
The salt doesn't heat up the ice. It just alters the chemistry so that the ice melts at a lower temperature. The water's doing the exact same thing to the rock deep in the earth.
That is a brilliant comparison. The water hits the mantle, lowers its melting point, and the solid rock promptly begins to melt into magma.
That is wild.
This specific process is responsible for the Pacific Ring of Fire. Almost every famous volcano you can name, Mount St. Helens, Mount Fuji, Krakatoa, they were all born because the ocean floor is literally sweating water into the deep earth.
The ocean floor sweating water into the mantle to create liquid rock. That is such a wild visual.
It really is.
So that's decompression and water. There's a third way to melt rock too, right?
Yeah.
One that doesn't rely on plate boundaries at all.
Right. The third mechanism is called a hotspot.
A hotspot.
Yes. This is when a plume of unusually hot, buoyant material rises up from the very deep mantle way down near the Earth's core.
Okay.
It acts almost like a geological blowtorch. It is so intensely hot that it simply melts its way right through the tectonic plate sitting above it.
Just burns right through.
Exactly. Hawaii is the classic textbook case here.
Right. And because the tectonic plate is constantly, slowly moving over time, but the blowtorch plume underneath stays in one fixed place, you get a line of volcanoes.
Spot on.
The volcano directly over the hotspot is active, but as the plate carries it away from the heat source, it dies out, and a new one forms behind it.
Which perfectly explains why Hawaii is a chain of islands.
Oh, that makes so much sense.
Yeah, the Hawaiian Emperor Seamount Chain is literally a geological record of the Pacific Plate moving over a stationary hotspot for tens of millions of years.
Wow.
Yellowstone is another prime example of a hotspot, but it sits directly over a massive plume erupting through a thick continental plate instead of a thin oceanic one.
Which, that changes the chemistry of the magma entirely, doesn't it?
It absolutely does.
And this brings us to a really crucial distinction for you guys listening. Once the rock is melted, whether by dropping pressure, adding water, or using a blowtorch, why do some volcanoes just gently ooze rivers of lava that tourists can practically walk right up to, while other volcanoes violently, catastrophically explode?
Yeah, the difference between a gentle ooze and a massive explosion all comes down to magma composition, specifically a substance called silica.
Right, silica, which is just all that silicon and oxygen binding together.
Exactly.
And when you have high silica content, those molecules link up into extensive chemical chains and networks, right?
Yeah.
It basically turns the magma into a highly viscous, sticky paste.
Yep.
But when the silica is low, the magma stays incredibly runny, almost like syrup.
Right, and we call that runny, low silica magma basalt.
Okay, basalt.
The stiff, high silica magma is usually called rhyolite or andesite. But here's the thing. Viscosity alone doesn't cause an explosion. You also need immense pressure.
So where does the pressure come from?
That is where dissolved gases enter the equation. Magma contains massive amounts of dissolved gases, primarily water vapor and carbon dioxide.
Okay.
Deep underground, the immense pressure keeps those gases perfectly dissolved in the liquid rock. They are invisible. But as that magma rises toward the surface, the pressure drops.
It's the soda bottle effect. Like, while the cap is on tight, a warm, fizzy soda looks perfectly still because the pressure is keeping all that carbon dioxide dissolved in the liquid.
Right.
But the second you twist the cap and release the pressure, all those gas bubbles instantly form out of solution and race to the top.
Now, combine that fizzy soda effect with the thickness of the magma we just talked about, and you unlock the physics of a volcanic explosion.
Oh, I see where this is going.
Yeah. If you have runny, low silica magma, like in Hawaii, the bubbles form, but because the liquid is so thin, they easily slip right through it and escape into the air.
The gas vents out naturally.
Exactly. You get beautiful, dramatic lava fountains and glowing rivers. The internal pressure of the Earth is released gracefully.
But if you have that thick, highly networked, high silica magma, the bubbles form, but they can't travel through the paste.
No, they can't.
They get completely trapped.
They're completely locked in. But the gas is still expanding as the magma continues to rise and the pressure drops further. So unimaginable pressure builds up inside the magma itself, pushing outward against this stiff, unyielding rock. Eventually, it reaches a breaking point.
And it just blows.
The rock fails catastrophically. The magma is torn apart from the inside out by its own expanding gas. It fragments instantly into tiny razor-sharp pieces of ash and pumice and is blasted out of the vent at supersonic speeds.
See, this completely reframes the danger for me. The difference between a beautiful lava flow and a mountain-destroying explosion has very little to do with how hot the magma is.
Almost nothing to do with temperature, yeah.
It is entirely about whether the expanding gas can escape gracefully or whether it gets trapped in a high silica paste until the whole system ruptures.
And this highlights exactly why subduction zone volcanoes, the ones on the Ring of Fire created by water, are so incredibly dangerous.
Because they have more silica.
Yes. When magma rises through thick continental crust, it melts some of that crust and absorbs vast amounts of silica. So subduction zones produce exactly that sticky, gas-charged magma that is prime for violent explosions.
Which means we really need to rethink volcanic hazards entirely. Because, you hear volcano and you instinctively think lava.
Of course.
But lava flows are basically the least of your worries in an explosive eruption.
Absolutely. I mean, lava flows destroy property, certainly. They crush houses, bury roads, and permanently alter landscapes.
But they don't really catch people off guard.
No, they rarely kill people, simply because they move slowly enough that you can usually just walk away from them. The deadliest direct product of an explosive eruption is something else entirely. The pyroclastic flow.
Just the name is terrifying. A pyroclastic flow is essentially an avalanche of superheated gas, volcanic ash, and pulverized rock. Right?
Yes, it behaves like a heavy boiling fluid, racing down the flanks of the volcano at speeds well over 100 kilometers per hour.
Over 100 kilometers an hour.
And the temperature inside that cloud is hundreds of degrees Celsius.
So you can't outrun it, and you can't survive it.
Not at all. The sheer density of it is the critical factor. Because it is so heavily laden with fragmented rock and ash, it is much denser than the surrounding air.
So it doesn't just go up into the sky?
No, it doesn't float up. Gravity pulls it violently down, and it funnels directly into valleys and low-lying areas. There's absolutely no outrunning a pyroclastic flow and no surviving being caught in one.
This is exactly what happened to Pompeii, wasn't it?
Yes. This is the exact phenomenon that buried the Roman cities of Pompeii and Herculaneum in 79 AD.
But the threat to human life doesn't stop when the eruption ends, or even with the initial blast radius. There's a secondary hazard called a lahar, and those often travel much further than the pyroclastic flows.
Lahars are terrifyingly destructive.
What are they exactly?
A lahar is a volcanic mudflow. During an explosive eruption, huge amounts of fine volcanic ash fall in the surrounding landscape, right?
Right.
If that ash mixes with a large volume of water, which could come from torrential rains or, very commonly, from the extreme heat of the eruption instantly melting snow and ice at the volcano's summit, it turns into a heavy, flowing slurry.
And it's crucial to visualize this correctly. We aren't just talking about a muddy river here. The closest analogy for a lahar is fast-moving wet concrete.
That is exactly what it's like.
It has the mass and the density to carry entire boulders, uproot giant trees, and completely sweep away bridges and reinforce concrete buildings as if they were made of paper.
And just like pyroclastic flows, lahars funnel into river systems. But they can travel much, much further, striking settlements dozens of kilometers away, sometimes hours or even days after the actual eruption has peaked.
I think the most devastating modern example of this was the 1985 eruption of Nevado del Ruiz in Colombia, right?
Yes. The Armero tragedy.
Armero is the textbook tragedy for this, because from what I understand, the town wasn't even on the mountain. The people living there probably thought they were perfectly safe from a volcano that was nearly 50 kilometers away.
They did. That geographical distance offered a terrible false sense of security. The eruption itself was comparatively modest, actually.
Really?
Yeah. But the heat melted a substantial portion of the mountain's summit glacier. That immense volume of water mixed with fresh ash and created colossal lahars that roared down the river valleys in the dark.
In the middle of the night.
They hit the town of Armero in the dead of night, killing over 20,000 people. It remains a stark, heartbreaking reminder that you do not need to live on the slopes of a volcano to be in its direct path.
It's just devastating. A lahar can wipe out a valley tens of kilometers away, but when we look at the really massive explosive eruptions, the impacts scale up exponentially. Like they can literally reach the stratosphere and alter the entire planet's climate.
This is where a localized geological hazard becomes a global meteorological event.
How does that happen?
Well, when a very large explosive eruption occurs, it doesn't just blast rock and ash. It injects millions of tons of sulfur dioxide gas straight up into the stratosphere.
Okay, sulfur dioxide.
Once it reaches that altitude, the sulfur dioxide reacts with water vapor to form tiny sulfate droplets, which are known as aerosols.
And the stratosphere is situated way above where our normal weather systems operate, right? There are no rain clouds up there to wash anything away.
Precisely why it matters so much. Because there is no precipitation in the stratosphere to scrub these tiny droplets out of the air, they just persist.
They just hang out up there.
Yeah, and high-altitude winds rapidly spread them around the entire globe, creating this thin chemical veil.
And what does that veil do?
These droplets act like billions of tiny mirrors. They reflect a portion of the incoming sunlight right back out into space before it can warm the Earth's surface.
So it literally blocks the sun.
The inevitable result is global cooling, which can last for a year or two until the aerosols finally settle out.
We actually saw a modern preview of this when Mount Pinatubo in the Philippines erupted in 1991, right?
Oh.
It injected so much sulfur into the stratosphere that it measurably cooled the global average temperature by roughly 0.5 degree Celsius for a couple of years.
We did, but honestly, Pinatubo was mild compared to historical extremes.
Really?
Oh, yeah.
Yeah.
Mount Tambora in Indonesia, which erupted in 1815, was orders of magnitude more powerful. That blast produced an atmospheric veil so dense it caused what historically became known as the year without a summer.
The downstream human impacts of Tambora are staggering to think about. You had widespread crop failures across the entire northern hemisphere. It literally snowed in New England in June.
People were starving in Europe because the harvests failed.
And it even bled into culture. Like Mary Shelley famously wrote Frankenstein because she and her friends were trapped indoors in Switzerland by the incessant, gloomy, unseasonal weather.
Right.
I mean, a mountain blowing its top in Indonesia directly caused famine and influenced literature in Europe. That is crazy.
The global interconnectedness is profound.
Okay.
Which brings us to the ultimate extreme of explosive volcanism. Eruptions so massive they defy our normal concept of what a volcano even looks like.
The supervolcanoes. The term gets thrown around a lot in disaster movies.
Yeah.
Usually alongside like a giant countdown clock.
It does. While supervolcano is a bit of an informal media term, volcanologists do use it to categorize eruptions at the very top of the volcanic explosivity index.
So what qualifies as a supervolcano?
Specifically, singular events that eject more than 1,000 cubic kilometers of fragmented material.
1,000 cubic kilometers. I can't even picture that.
That volume is almost incomprehensible. A single eruption of that size would bury an area the size of a large country in feet of ash. But the physical structure left behind is actually fascinating because these systems don't build towering, majestic, cone-shaped mountains.
Because they physically can't, right?
Yeah.
The eruption is so massive it empties the underground magma chamber so comprehensively and so quickly. That the rock roof of the chamber has nothing left to support its weight.
Exactly.
The ground itself simply collapses downward into the void.
You don't get a mountain blowing its top. You get the ground falling in, leaving a vast, bowl-shaped depression in the earth called a caldera.
A caldera?
Yes. Yellowstone is a classic caldera system. Its main crater is roughly 50 by 70 kilometers across. You can literally drive through it and barely realize you are inside a volcano.
Because it's so big.
Right. And the Togo caldera in Sumatra, formed by an eruption around 74,000 years ago, was even larger.
Okay, I am so glad we are landing on Yellowstone. I constantly see headlines declaring that the Yellowstone supervolcano is overdue for a catastrophic eruption that's going to, wipe out half the continent. Let's apply some logic to this. Is Yellowstone actually overdue?
It is absolutely not overdue, and we need to treat those headlines with extreme skepticism.
Thank you.
People look at the geological record, they see that Yellowstone has produced massive eruptions on a rough average of every 600,000 to 800,000 years, and they treat that average like a bus timetable.
But the Earth doesn't have a calendar on its wall. It doesn't care that it's been 600,000 years since the last major event.
Exactly. The physics of an eruption are driven by thresholds, not time.
Thresholds. Like,
an eruption only occurs when sufficient eruptible magma has accumulated, and the internal gas pressure exceeds the structural strength of the rock holding it in. Right now, there is zero geophysical evidence that Yellowstone is preparing to erupt.
even with all the geysers and earthquakes.
Yes, the ground deforms, and there are periodic earthquake swarms, but that is entirely within the normal baseline behavior for a restless, living caldera system that is slowly cooling and shifting.
Okay, well, that is deeply comforting. But it does raise a practical question. Since we know volcanoes operate on physical thresholds rather than a neat timetable, do we actually have reliable ways of knowing when those thresholds are being crossed? Can we predict when a volcano is actually waking up?
The science of forecasting is advancing rapidly. While predicting the exact timing of earthquakes remains incredibly difficult, volcanoes are actually remarkably cooperative.
Really? How so?
Well, as we discussed earlier, eruptions begin with new magma moving up from deep underground. That movement produces very clear physical warning signs on the surface.
Right, because thousands of tons of liquid rock cannot force its way upward without literally shoving the existing rock out of its way.
Exactly. And that shoving fractures the crust, causing highly distinctive swarms of small earthquakes.
Okay, so you watch for earthquakes.
That's one sign. The immense physical pressure of the rising magma also causes the ground surface itself to inflate and bulge upward.
The ground actually swells.
It does. We can measure this deformation with incredible precision. Scientists use GPS stations on the mountain and satellites utilizing radar interferometry, which basically bounce signals off the ground to measure changes in elevation down to the millimeter.
That is amazing. So you have the ground shaking, you have the mountain literally swelling up like a balloon. And I imagine the gases are changing too as that magma gets closer to the surface and the pressure drops.
Yes. You measure dramatic changes in both the composition and the sheer volume of gases venting from the crater, particularly increases in carbon dioxide and sulfur dioxide.
So putting it all together gives you a warning.
Monitoring these three indicators, seismicity, ground deformation, and gas emissions, has led to incredible, genuine successes in forecasting. Returning to the 1991 eruption of Mount Pinatubo, scientists tracked those exact warning signs perfectly.
And they evacuated in time?
They forecasted the eruption in time to evacuate tens of thousands of people, saving countless lives. Volcanology isn't perfectly precise, and volcanoes can certainly be deceptive, but the warning signs are real, physical, and readable.
It really makes you wonder why humans have historically chosen to live so close to them, given the risks. But there's a powerful incentive, isn't there?
There is.
Because volcanic ash breaks down into some of the most incredibly fertile, nutrient-dense agricultural soil on the planet. For thousands of years, the risk of a potential eruption was far outweighed by the immediate reward of abundant food.
It's a fundamental human trade-off. We build our societies where the resources are, and we tend to possess a very short-term memory when it comes to geological time.
Yeah, that makes sense. Let's bring this reality home and look at a specific geographic context, like Australia. The Australian mainland doesn't have any currently active volcanoes. It sits safely right smack in the middle of its tectonic plate, far away from the subduction zones of the Ring of Fire. But there is a massive volcanic province stretching across western Victoria and southeast South Australia. And geologists are very careful not to call it dead. They call it dormant.
That's a crucial scientific distinction. Dead implies the heat source is permanently gone, that the engine is completely cold.
Right.
Dormant simply means it is sleeping. The most recent eruptions in that Australian volcanic province happened just a few thousand years ago.
Which, to human civilization, a few thousand years sounds like ancient history. But to the Earth.
To the Earth, a few thousand years is barely a blink of an eye. Geologically speaking, that is incredibly recent. The underlying mantle dynamics haven't vanished. There is every reason to believe magma will eventually find its way to the surface in Australia again. Just a matter of geological time.
Wow. Well, pulling all of this together, we've gone from the deepest, most inaccessible rocks to the upper reaches of the stratosphere. We've learned that underneath a volcano sits a mostly solid slushy of crystalline rock.
Yep, the slushy.
And to melt it, the Earth has to drop the pressure by pulling plates apart, turn a blowtorch hotspot on it, or force water out of a subducting plate to lower its melting point.
And we explored how the personality of the eruption, whether it flows gently or explodes catastrophically, is entirely dictated by how much sticky silica is in the magma.
Right.
That silica determines whether the fizzy, expanding gases can safely escape, or whether they get trapped until the rock is literally blown apart.
And if it does blow apart, you aren't running from a river of lava. You are facing pyroclastic flows of superheated ash hugging the ground, lahars roaring down river valleys with the force of wet concrete.
And if the eruption is massive enough, a veil of sulfate aerosols that can plunge the entire globe into a cold, dark year without a summer.
It really highlights how deeply interconnected the solid Earth, the oceans, the atmosphere, and human history truly are.
It's all one massive system.
It is. I want to leave you all with a final thought to mull over, building on where we started this whole journey today. The next time you are out for a walk or at a garden center, and you pick up a piece of light, airy pumice or a dark, heavy basaltic rock, realize that you aren't just holding a standard stone.
No, you're not.
Think about the incredible physical journey it took to get to your hand. You are holding a rare, direct messenger from a hidden, completely alien world, thousands of kilometers beneath our feet. It's a place humanity will never, ever be able to visit. But every so often, that alien world reaches up to the surface just to remind us it is there,